So, hello everyone, I'm Mia-Eli from Deltamarin, and I'm here to present some results from our ongoing EU project CHEK. So, let us begin. I was first actually thinking to a little bit introduce our project, because maybe you're not aware of that entirely, and then tell something about the maritime decarbonization overall, before going into some of the ongoing results in the project. So, first of all, Project CHEK. Well, as every development project, the abbreviation comes from actually a rather long sentence. CHEK is about decarbonizing long-distance shipping by enabling key technology symbiosis on real vessel concept designs. Okay, what does that mean? So we are actually developing and working with two very different kind of ships. So we have a Kamsarmax size bulker, and then we have a Meraviglia class type of cruise ship. And we are looking basically at real vessels as our kind of model of how they operate. So we are actually looking at real and realistic operational profiles. And then we generate new concepts for this size of ships. And we work with very multiple, let's say, energy saving technologies, and also want to aim for decarbonizing these designs. So the project aims actually, we have pretty ambitious goals. So we are aiming to reduce the greenhouse gas emissions by 99%. And before kind of coming to that goal, so we want to save energy 40 to 50%. And then also we want to, at the same time, reduce the black carbon emissions by over 95%. So how do we do that? So let me tell you something about that. Who are we in Project CHEK? Well, we are actually, as typical in EU projects, so we are many companies here. So personally, I'm coming from Deltamarin. We are the ship designers in the project. We have also Lloyd's Register here, the Classification Society. And of course, since we are working on realistic ship concepts, so we have the end users here, we have Cargill representing the operation of the bulk carrier, then we have MSC Cruises here, we have researchers, we have Vasa University here, we have World Maritime University, where I'm also visiting at the moment, making this recording. And then we have a lot of technologies. We have Wärtsilä providing of course, the engine information in the project, but also providing kind of much input for the hybridization of the powertrain of the ships and looking at propulsion technologies. We have Silverstream technologies, air lubrication. We have climate and waste heat recovery. We have Hasitec, ultrasound, hull fouling prevention, and Yara Marine and bar technologies for bringing the wind to the ship. So we are a big consortium, big goals. So let's talk a little bit about the decarbonization. If we think about maritime decarbonization, so it is a hybrid of operational. First of all, we can save energy. We can reduce energy use of the ships with operational means. We can improve the designs. We can have these technologies. But then also we need the fuels, we need the kind of compliant fuels to make the last part of it. And the thing, of course, the whole how to get there. And so we have also now, we have rules, we have of course national rules, we have EU level legislation under development, but also the IMO rules regarding maritime decarbonization. So they are also under quite rigorous development at the moment. So just to bring here something from the IMO side, one of the latest newly introduced rules within the maritime decarbonization is the Carbon Intensity Index, CII. So here just as an example, so this is one of the metrics we are also, let's say, following within this project. Our aim, of course, is to save energy also in absolute means, so we are modeling and recording the absolute, let's say, fuel savings, but also we follow the CII metrics, which is then actually metrics for ship energy efficiency, so that it's given in grams of emitted CO2 per ship, let's say cargo carrying capacity and nautical miles. So actually we have in the CII metrics, we have the distance that the ship is traveling within 1 year, and then the fuel consumption multiplied with the carbon factor. So that is how it's calculated, and then how the rule setup works is that every ship will then get a rating based on their calculated CII ranging from A to E class, and this is a moving target. So basically the goal for CII, so the kind of goal to be in the average, the class C, so it's getting tighter every year. So in that sense, this is very interesting metrics for us to follow in the project as well. Then just to kind of a little bit then discuss about the technical side of things. So what we're looking at here is a Sankey diagram. Actually, it's taken from the earlier modelings in this CHEK project, visualizing a little bit how the energy the fuel energy, which is taken on board the bulk carrier ship in this case, how the energy is distributed. So not really going into those details right now, but just kind of saying something regarding this energy efficiency, that if we want to save technically fuel on board a ship, so we can just simplify it in a couple of things. So if we want to minimize or reduce the fuel consumption on board, which would be then here pictured with this green part, the fuel energy, so making that smaller, so of course we can try to reduce the process energy consumption. In this case, this blue part is representing the propulsion. So in this kind of a cargo ship, of course, propulsion is representing major energy consumer here. So however we are able to reduce that consumption, so then actually the whole fuel consumption gets smaller and smaller in the ship, as we can actually visually also imagine here with this picture. But we have also other energy consumers. We have the hotel, ship auxiliary processes, and we have also certain heat consumers on board. And if we think about the cruise ship case, which we are also working in CHEK, so there actually this whole picture looks very different, because there we have a lot of other processes than propulsion as well. But anyway, so this is one side of energy savings. So let's try to kind of minimize the consumption with various ways. But then there's the other side of things also, that if we can, let's keep the energy demand the same, but if we can have an efficient power plant, so that is of course the other way to improve also the energy efficiency of the ship, so that we would increase the power plant efficiency, the kind of energy conversion efficiency of the main fuel we are taking on board. So both these of course are the means, and we are exploring actually both sides in Project CHEK. And then of course whatever fuel we're using here, so then that is also having impact to all of these processes. So here is just a big picture, a lot of details, let's not focus on them, but I just wanted to highlight that what does it mean when we introduce a new fuel to a design where we are maybe more used to certain traditional alternative. So of course it's a lot about the tank capacity, the volumes and the materials and everything related to that. It's about the chosen engine or prime mover configuration. But then of course there's a lot of details around this. There's the whole safety aspect of things. New fuels, new engines, they need also different kind of auxiliary processes. Then there's of course, let's say some also opportunities. If we have clean fuels, we also have more cleaner, let's say, exhaust gases with different type of engines or let's say power producers. We can also change the whole structure of how the, let's say, waste heat processes are distributed within the ship. So in a way, all of this picture is also in the background when we are improving the ship, let's say, emission performance. But we could a little bit move back to Project CHEK. So how the project is actually going on regarding these case ship developments. So we are developing the case vessels, these conceptual vessels, on 3 different, let's say, model generations. So we at Deltamarin, we are responsible for producing these results, putting it all together. So to say, so we are doing this in 3 generations. So we are modeling, our first model generation was called digital prototype, where we mainly had, we were collecting quite much information of the existing vessels operating so that we would understand the operational characteristics. So we were taking a lot of actually measurement data of both vessels and then running simulations with changing certain parameters. There's changing the engines and that kind of things. But then these results, what I'm now going to talk about, it's the digital master phase, where we already have generated new hulls, for example, for the vessels, and then we are kind of running through the results, and I'm going to be talking in the next part a little bit about the components in the digital models. But then we will still have the final round of modeling where we are going a little bit more into details, the so-called digital twin. In this project, of course, since we are still working fully with conceptual ships, so we are not, of course, able to produce a digital twin of those ships because we are not building those ships within this 3-year project. But let's see a little bit. So as said, we are now in the digital master phase. So if that was kind of the project timeline a little bit, so what is in the digital tools, so how we see it, that's because a part of the Project CHEK is that we are also building these digital tools, so we can of course use them to any ship. So we like to see digital modeling rather than one big tool or item, so we see it in more like layers. So in this digital design, so one kind of key layer, of course, is the ship hull and structural model. Okay, since we are the designer here, so we have our own Deltamarinized names. So Deltaway is our, what we call the kind of main design, the hull and volume model of the ship. But then the second stage of the digital modeling is the Delta Seas, where actually we take this hull model in vacuum, so we take it and combine it to digital seas. So basically we combine the external forces caused by the weather and of course like propulsion efficiencies, so that we can produce as realistic propulsion profile as possible for the ship. And then the final layer is what we call here Delta Key, which is the energy model then. So we combine basically this digital propulsion profile to the ship machinery and to ship energy consumers, and then we can calculate those fuel consumption and environmental indicators. So here's another little bit deep dive to this Delta Key and how in this Project CHEK we are working with these models. So basically this green part, Delta Key, so here, as I said, so we are taking input from the propulsion side, and then we are having their combination of these energy efficiency technologies we study, and of course the whole ship main energy consumers. And then we calculate, let's say, various key performance indicators for the project. So we start from the energies, look at the fuel consumption, and then also we calculate this, as I mentioned, this CII, for example, indicator, certain design indicators like energy efficiency design index we also calculate in the beginning of this process. And then also we are looking at heat process efficiencies and that kind of things. So, but I guess everybody is a little bit dying to know what can we do with all these technologies. So let me just also bring a little bit insight of these intermediate results. So we look at our bulk carrier example here from the digital master phase. So this is not still the final results, but just to show a little bit. So first of all, here's some main dimensions of the ship. So we have this Kamsarmax size bulker with certain design, let's say design speed, 14 knots and so on. And based on all this modeling, so actually as mentioned, so how we are then simulating these propulsion profiles, so we are not just taking that 14 knot speed and putting a fixed sea margin, but we are actually collecting together with Cargill and our reference ship, we take typical operational areas and profiles, and then there has been quite big work actually making routing for them and collecting weather data from this Copernicus database, running that several times in the past with the past weather, so that we get a realistic idea of the weather along the route, and that way we can calculate a little bit more, let's say, dynamic propulsion profile for the ship. And here we can see some of the big picture values. So actually the vessel in this profile, so for example the sea time is about 60%, and the vessel is then staying in port also considerable amount of time. Something about the machinery. So we have here the goal is to actually explore as it said in the Project CHEK name, so we are looking at actually innovative combination of many technologies and the design. So we also will need eventually a very flexible machinery for enabling this kind of operation. So we look as a baseline, we have a two-stroke machinery, but we also then look and explore the machinery with four-stroke and with controllable pitch propeller, for example, and having shaft generators and batteries also in the powertrain. So this work is ongoing. For this current model generation, what we are looking at here, so we are not yet focusing so much on this fuel flexible four-stroke configuration, but it's that is actually part of the next generation, where we are actually cooperating together with Wärtsilä, so that we actually get a better and more realistic combination from them of the CPP propeller efficiency and the engine efficiency packaged in a one nice model, which we are then taking into our simulation models. So in that sense, these results, what we see here, is not final yet, but it's giving some first taste. So just to show also what kind of things we are modeling here, we will be repeating this also in the next round. So we are having our benchmark conceptual design with the two-stroke engine here, and then we are running the same with just taking the same but putting here a four-stroke engine machinery. And then we are looking at what can we do if the ship has shore power in every port available. How about if we add their organic cranking cycles and these all kind of technologies are then run with this four-stroke engine configuration. Then we add as a single item air lubrication estimated by Silverstream. Then we have two sails provided by BAR Technologies and Deltamarin. So the kind of digital model, the estimation, what these sails put to this kind of digital weather profile, what they can do. And then we are also actually studying gauge rudder in this project. For the time being, this is just assumed to be a fixed percentage saving, since we don't yet have more exact, let's say, model that we could utilize in our simulation. And then we run basically this configuration with this biogas as main fuel, altering some parameters, of course, in the machinery and in the heat consumption of the vessel and so on. And then we run a combination, which is kind of the main point of the check, to run combination of these things, both with and without this biogas as fuel. So when we look at a little bit, probably we shouldn't be so much now staying in every single figure here, but just to show what kind of things we are calculating here. So of course in the simulations we look at a lot of things. One of the leading things, of course, is the entire fuel consumption. So we are looking at fuel distributed for different consumers, main engines, auxiliary engines, boilers. We get a certain baseline consumption. Then as a designer and when we want to improve things, we look at issues like a power plant efficiency for the entire ship. We can look at that also, the loadings for the engines, and make some conclusions from that, and the energies for the different consumers. And here when we kind of switch from the 2-stroke to 4-stroke, as said, these are not kind of the final results by any means yet, but we can see that when we have the shaft generator, so we are reducing the auxiliary engine use in this case. So for example, here we are not calculating the maintenance hours, but that would be also one item to kind of focus on. We also can see that the oil-fired boiler consumption is less with the 4-stroke engine configuration. So there's a lot of interactions already, even if kind of having this more simplified engine modeling. Then when we add actually organic cranking cycles, we can just point out some things what we spotted in the results. That for instance, there was actually pretty large change in the energy efficiency. So actually bringing this waste heat recovery system for this configuration, so it actually meant that we were able to switch off one of the 4-stroke engines, and we reached much better engine loadings and power plant efficiencies. And then of course the organic cranking cycles themselves also produced part of the electricity for the ship. So we can see there's a lot of interactions already there happening with this combo. And we can then kind of quantify for each single improvement. We have there the aerial application. And then we have the sales over here. And all these results, of course, so they are calculated for this average year. So what we can maybe also point out that with these preliminary results, so for example, if we look at the time at sea with the sales, so we could see that it is, I think it will, for every day at sea, so we could see over 3 tons of fuel saved per each day with this technology. And then we can also observe certain similar things that we change the engine loads and we change the power plant efficiencies. And then when we put it all together, so of course it's not a sum of each individual improvement, but it is something else. So therefore it's important to actually model these things in symbiosis and then figure out that how should we adjust the sizing of these components and the machinery so that it kind of brings out the best of all the technologies. So that's what we are doing in Project CHEK. And to make some of the concluding, let's say, statements of the results, so we can also look at this from the CII perspective. If we remember the CII, so of course this is not linear to the fuel consumption, especially in cruise ship type of ships, but in bulker it actually is pretty equivalent, I would say, these carbon intensity index improvements. So what we can just say from these results, we were looking at first, because now in the current rule framework, for example, when we introduced this biogas as fuel, so in the CII framework, it doesn't yet get any benefit from being kind of something different than liquefied natural gas. So it doesn't get this kind of environmental benefit, but we know that the rules are developing towards well-to-wake approach. So there we can just speculate that the end result will be that we are actually reaching our goal of this decarbonization in Project CHEK with introducing this biogas. But maybe one item to look at here is that already with this energy-saving technology mix and design mix, and assuming that we can also reduce the vessel fouling with this technology, what we are implementing here is that we can see that this CII will be, or this vessel with this technology mix would be more likely compliant for the next decades to come. So this is one of the things we see. So maybe just to summarize a little bit what we saw here and what we also kind of, what are we doing in the Project CHEK. Well, first of all, so we could see that, you know, even implementing one item at a time, so it is not trivial actually when you bring a new technology on board that what happens, because there's so many, let's say, there's so many interconnections between processes that we have to simulate it all. We have to see what the engines are, you know, what the actual propulsion profile is, so that we can see the full impact. And one of the conclusions already said is that it's definitely possible to reach a design which will be compliant in the kind of this CII, this carbon intensity index rule framework, probably decades to come. But of course, we already know, or we know now only what will happen in this rule framework until 2026. Then we can only speculate how this index and the rule development will go further. So in the Project CHEK, what we are doing now, as we see some pictures here, so actually in CHEK, so we will of course, we as the designers will continue to model the ship to our next round, and it will be actually then having much more information, much more numerical, let's say, validation and details of the technologies, how they work, because some of the CHEK technologies will be tested in lab and we are getting those values to complement our models. But then actually there are several technologies such as this anti-fouling technology, so that is, there are some test patches and some test installations in both ship types, so we will learn something from that as well. And then maybe some of you have already seen that we have a vessel sailing within this EU Project CHEK, so bulk carrier with 2 sails installed, so by Bar Technologies and Deltamarin. So we will of course then also see the performance of that vessel, and that will be also very interesting to kind of compare that to the simulated results. So definitely I think that's the Project CHEK. So we are here kind of visualizing and also modeling how far we can get with the energy saving technologies, and eventually then finding ways how to decarbonize. So thank you.